Howdy, and welcome back to the new Robotics workshop. Today we're going to learn about power electronics. These concepts will apply to all kinds of robots, but since we're focused on our workshop rover, we're going to use that for all of our examples. We'll start out by discussing some electrical engineering theory, then we're going to design our rover's power circuit on paper, and we'll wrap up by building and installing it in our rover. Let's get into it. Before we begin designing our circuit, we're going to recap a few key electrical concepts. Usually, when we're trying to measure electricity or quantify how much of it there is, we use three key terms. The first is voltage. Think of this like the pressure that drives electricity through a circuit. The unit for that is volts, and we represent it in an equation with a V. The second is current. This is how much electricity is actually moving through our circuit. The unit for that is amps, and we represent it in equations with an I. The last is power. This is a bit of a tricky concept, but it's referring to how quickly we are using or transferring energy with our circuit. The unit we use for this is watts, and we represent it in equations with a P. There's a lot to learn about circuits, and if circuits are new to you, there are a lot of great resources out there that explain these concepts in more detail. For now though, we're going to focus on three key things that will be useful for creating our robot circuit. First is relationship between voltage, current, and power. This relationship is described by the equation power equals current times voltage. The second key concept is that for the electrical components we use, the supply voltage they require is usually the same, but the current they pull may be different. A good example is a microcontroller and a sensor may both run at 5 volts, but that microcontroller is probably going to pull more current than that sensor does. Last, it's important to understand that when a power supply gives a power or current rating, that is the maximum that it can safely supply. When a device gives a power or current rating, that's the maximum it will ever pull. To build safe and effective robots, we need to pay close attention to these three key points. When we fail to give a device the power it needs, it may work poorly or not at all. But when we exceed the ratings of the power supply, it may break, get hot, or even catch fire. We need to be careful to select our batteries, components, and even our wires so that they work safely and effectively together. The first thing we'll do in designing our rover's power circuit is select the voltages it should operate at. A lot of commercial off-the-shelf components, including many of the ones we're using in this workshop rover, operate at 5 volts, and so we know we're going to want 5 volts. The challenge is in finding a 5-volt battery. Because of chemistry reasons, they don't really exist. But even if they did, our motors down here are going to want 12 volts. So we need to find a way of getting 5 volts from a battery that can't supply 5 volts. The solution to this problem is to use a voltage regulator. A voltage regulator is a component that can take a variety of usually higher input voltages and convert it to, in our case, a steady 5 volts. That solves our battery chemistry problem, but now we need to know, what do we want on the other side of this regulator? What do we want our input voltage to be? We'll call the input voltage to our regulator the supply voltage. The best way to choose our supply voltage is to consider what else it could be used for beyond feeding our regulator. Our motors down here run at 12 volts, and conveniently a 3-cell LiPo battery produces approximately 12 volts. So we'll select 12 volts as our supply voltage, branch some off for the motors, and send the rest to the regulator to feed the 5-volt components. With our supply voltage selected, we figured out more or less how we're going to send power to all of our components. You'll notice there's a little component down here called a motor driver that we haven't talked about yet. We're going to discuss that in detail in the next lesson, but for now, just trust me that that needs to be there. For now, we'll move on to talking about the currents in our system. With the operating voltages in our circuit selected, we now need to consider the currents we'll be dealing with. The currents flowing through our circuit are going to impact a lot of our design decisions, particularly the exact components we select. If we select the wrong components, our circuit could get hot, break, or even catch fire. It's very important to be aware of the currents flowing through your circuits. Luckily, designing around the currents your components draw isn't all that hard. We're great place to start is by listing all of the currents that your 5-volt components draw. You can usually find this information in data sheets, which are documents provided by the manufacturer of your components that tell you all about how to use the parts you're buying. These data sheets are usually available through the retailer who sold you the part. Here's a list of all of the 5-volt components on our workshop rover, including their estimated current draw. The current that we're going to pull from our 5-volt regulator is simply the sum of all these values. In this case, 66.2 milliamps. In our calculations, we're going to round that up to 100 milliamps just to be thorough. Remember point number 1 under power concepts? That was the relationship between power, voltage, and current. We can use this relationship to determine how much power our voltage regulator needs to provide. We know our regulator needs to provide 0.1 amps of current, and it needs to do it at 5 volts. Therefore, we can calculate our voltage regulator needs to provide a ½ watt of power. Luckily, this isn't much power, and there are a lot of 5-volt regulators out there capable of doing it. Oh look, there's one in your kit. We can also use this power relationship to determine how much current our 5-volt regulator will draw from our battery. The law of conservation of energy tells us that if we pull a ½ watt of power out of our regulator, we need to put a ½ watt of power into it. If we need to put a ½ watt of power into the voltage regulator, and we need to do it at 12 volts, then we need to supply 0.042 amps of current. Now this isn't exactly true because this assumes that our voltage regulator is 100% efficient, which it isn't. In our case, we're going to solve that problem by just rounding up to 0.05 amps and calling it a day. But if you want to be thorough, you can always look up efficiency specs for your regulator and do it the right way. So we know how much current our 5-volt components will draw, and we've chosen an appropriate voltage regulator. We've calculated how much current that voltage regulator will draw from the battery in order to supply those 5-volt components, but there's 2 more things hooked up to our battery, our 2 motors. In order to determine how much current is pulled from our battery, we'll need to figure out how much current the motors themselves pull. To do this, we need to go back to our data sheets. To be safe, we'll consider the worst case scenario, which occurs when the motors are stalled. That means the motors are set to their max speed setting, but they can't move, maybe because I'm holding the wheels still like this. In the motor data sheet, we can see that the stall current for our motor is 0.75 amps. We have 2 motors, so that means our motors together will pull 1.5 amps. Combine that with the pull from our 5-volt regulator, and our 12-volt battery will need to supply 1.15 amps total. Alright, we've determined we need a battery that can supply 1.55 amps at 12 volts. LiPo batteries are great at storing a lot of energy in a small space and then releasing that energy very quickly. This trait makes them great for robotics, but also dangerous. And so there's a few safety points that you should follow. First of all, be careful not to let your battery charge get too low. Later on, we're going to calculate an estimated runtime for our robot. Pay attention to that number, and if you notice your robot getting slower or seeming sluggish, you should charge the battery or replace it with a fresh one. Second, a LiPo battery that feels puffy or squishy when you squeeze it is unsafe to use. A damaged case is also unsafe. If a LiPo cell is exposed to air, it'll combust, and you might not be able to put the flames out. You don't want to puncture a LiPo battery, you don't want to short circuit a LiPo battery. If you have any reason to doubt the safety of a LiPo battery, I highly recommend you go find a battery disposal bin or take it to a safe battery disposal facility. If you have any reason to doubt the safety of a LiPo battery, I highly recommend you dispose of it safely at a battery disposal bin or a battery disposal facility. These warnings might make LiPos seem scary to use, but they're incredibly useful devices and are safe when treated with respect. I don't want to scare anyone, but I do want to impress on you what that respect means so you don't have to learn the hard way. With that disclaimer out of the way, let's get into some battery specs. A LiPo battery will usually list 3 specs. The first of these is the S number. This is the cell count of the battery. 1S is 1 cell, 2S is 2 cell, and so on. This tells you the voltage of the battery, because a LiPo cell is always going to be approximately 4 volts for chemistry reasons. And by stacking LiPo cells on top of each other, like this, we can create higher voltages, such as our approximately 12 volt battery that we're using in this workshop kit. The second spec is the battery capacity in milliamp hours. This tells you how much current you can draw from the battery to drain it fully in an hour. Our workshop rover has a 500 milliamp hour battery. This means that if we draw 1.55 amps from this battery, then we'll drain it in approximately a third of an hour, or about 20 minutes. The last spec a LiPo battery will often list is the discharge rating, or C number. This can be a bit of a strange unit to understand, but what it's telling you is if you multiply the battery capacity by the C number, you get the maximum current you can safely pull from the battery. We have a 500 milliamp hour battery with a 35 C number. So the maximum current we can safely pull is 17.5 amps, or well over 10 times the current we expect to pull from our battery. We can absolutely use this LiPo battery to power our robot as we develop code and troubleshoot it at the lab bench, but we know from our calculations that we're going to get about 20 minutes of runtime out of this thing. So if we don't want to be constantly charging it, it can be useful to power our robot with a benchtop power supply or something of that sort while we troubleshoot it and work on it. Figure out what tools you have at your disposal and choose what works best for you. At this point, we've performed some solid power calculations and designed an effective circuit for our rover. We're going to stick with this simple circuit for the purposes of our workshop rover, but there are a few other considerations you may want to entertain for more complex robotics designs in the future. All of our components need to be able to support the currents and voltages that are flowing through them. We've talked about that plenty at this point. But what we haven't talked about is that our wires and connectors also need to be able to support those currents flowing through the circuit. There are a lot of factors that affect whether or not a wire or connector is able to do this. Far too many to talk about here, but you can find tables that allow you to select proper wire gauges and specs that allow you to select proper connectors for your use case. In the future, you may want to consider incorporating fuses into your robot circuits. Fuses are parts that are designed to burn out and break when a certain current flows through them. As we've discussed, shorting LiPo batteries can lead to fires that are difficult to put out, so it can be useful to put a fuse just in front of your battery. If you short your battery at some point in the circuit, that fuse will burn out and prevent the LiPo from combusting. We can also use fuses to protect specific components from overcurrent, but on our small robot, that gets a little bit cumbersome, having a whole bunch of fuses in there. In our case, we have very affordable components, and it may be simpler just to swap them in and out if we break them. Last, let's talk about power switches. LiPo battery connectors are often intentionally difficult to unplug, and so it can be unwieldy to turn your robot on and off by removing the battery. Power switch is incredibly convenient when your robot bugs out and decides it wants to run away. And it can also help protect against shorts when you're unplugging or plugging in your battery. Before we start plugging components into our breadboard, we first need to assemble a few components. The first of these is the voltage regulator. You need the 5 volt regulator itself, the JST connector for the LiPo battery, and 4 jumper cables. I like to use orange for my 5 volt line and red for my 12 volt line. Brown and black are both ground. I'm going to start out by trimming the ends of these jumper cables. And once we've done that, we're going to strip all these jumper cables. Let's see what looks right. I'm going to guess 24 gauge. We're going to try that first. Beautiful. clean up our mess as we go. Alright, all of my parts should be prepped for this. So, you know what I'm going to do? I'm also going to prep the ends of this battery connector. This one I'm going to choose a slightly larger gauge. That appears to have worked nicely. That was 22. There we go. Lovely. Alright, I'm going to take my red and black wires. We're going to twist these ends together. Uh-oh. This may be a bit challenging. Don't be discouraged if you have to try a few times. But the goal is to get these nice and streamlined so that they'll go into these solder pads on the 5-volt regulator. Just like that. That's actually beautiful. Awesome. And so remember, these red lines, black lines are coming from the battery. So remember, these red lines and black lines are coming from the battery. So I want them on the inside of my voltage regulator. These jumper cables are for branching off 12-volt power to the motors, like we talked about doing in our circuit. Once I have those in, set this part down, and I am going to carefully solder these in place. Here, we're gonna turn it around. This might be easier. Let's check that went through. Nice, that's a good solder joint. Now let's do the red one. Lovely. You can see how it beat it up on top of that pad. And then as the pad got hot enough, it all flowed right in. We can check the other side and see that solder flowed all the way through the joint to the other side. Next, we're going to do a very similar thing with our remaining 2 jumper wires. Push them through. Fold. Be gentle. The wires are not as strong. They're missing that nice heavy gauge core from the battery connector. So you just got to be a little more gentle. But that's okay. We'll do the same thing. Heat it up, let it flow. Heat it up, and let it flow. Lovely. We have 4 beautiful solder joints. So now I'm going to do a few things just to kind of make this whole package look nice and tidy. I love to twist my wires together. Right. Now this side. Lovely. So another thing I really like to do is use heat shrink to keep my cables neat and tidy and to protect my 5-volt regulator. Let's snip off that. A little more. Beautiful. All I'm going to do is slide it over these jumper cable ends. Maybe a little tricky to get it go. It's a little bit of a snug fit. There we go. You want to make sure that these are positioned nicely next to each other. I'm going to do the same on this side. Lovely. And here we go. Try some of that. We're going to slip a bit of this over the regulator itself, like I said, to protect the regulator. Now, I didn't want to bring Space Grant's heat guns all the way out of the assembly lab to shoot this, so I am going to go heat shrink these items. Alright, and with a quick pass from the heat gun, I have a very neat and tidy package. Hopefully you can get a good look at that. If you're going to do this, be gentle with the heat gun. It can easily get hot enough to start melting these plastic crimp jackets. So take your time, there's no need to rush. I think taking the time to twist these cables and add these little heat shrink covers just makes your whole package look a lot neater, tidier. Aesthetics don't imply function, but the people who take the time to make their work look good also tend to take the time to do it right. For now, we're going to take this voltage regulator and we're going to set it aside. The next component we need to assemble is a lot less intensive. We need to solder header pins onto the motor driver board. There we go. In the prior lesson, we talked about using breadboards to help you solder things easily. We're going to do the same thing here. Let's see. Let's take the time to stick those header pins down on the breadboard at the right spacing and set your motor driver right on top of it like that. Now I'm going to go through and I'm going to solder all these pins. Went a little bit overboard on the solder for that pin. That's okay. Uh-oh. This is a good example of an issue you can have with soldering. I accidentally soldered these two pins together. That's not that big a deal. I'll show you how to fix that. What I've got here is a solder sucker. This is a tool that, like its name suggests, can suck up solder from a joint. You need to charge it by pressing I need to charge it by pressing this plunger down, and I release it with this button. What I'm going to do is I'm going to heat up this solder joint until the entire thing is liquid, and then I'm going to suck that solder right off. You can see it's fixed. Now I'm going to go through and I'm going to carefully solder the rest of these joints. There we go. Might try hitting some joints with a little more heat. Seems to help that one. Alright. I think those look a smidge better. Once I've soldered all these joints, I'm going to pull this piece right out of the breadboard. Be a little patient, be sure not to grab it when it's still hot from soldering. Next, we're going to place the motor driver on the breadboard. Make sure that this largest chip, this black one, is downward. We're going to press the left row of pins into D6 through 13 and the right row of pins into H6 through 13. We're probably going to need to remove this leftmost motor connector briefly in order to do this. Get that out of the way. D6 through 13, if we line that up properly, it'll go in exactly where we want it to. There we go. Again, that's left row of pins into D6 through 13 and right row into H6 through 13. Now that that's in place, I'm going to put this left motor connector back. We'll see there's just a smidgen of overlap between these two components. We'll call that a version 2 improvement. Now we're going to return to our 5-volt regulator. Let's take the jumper cables at the output of the voltage regulator, and we're going to plug it into the right power rails on this breadboard. Make sure that the brown goes into that blue rail and the orange goes into that red rail. This set of power rails is now my 5-volt bus. Any component that needs 5-volt power is going to take it from this set of power rails. Likewise, I'm going to take these red and black wires at the input of my voltage regulator. I'm going to plug them into my left set of power rails. These are now my this set of rails is now my 12-volt bus. And anything that needs 12-volt power is going to take it from these rails. Here's what it looks like properly placed on the breadboard. The last thing we need to do is to make the necessary connections to get 5-volt and 12-volt power where it needs to go. To do that, I've got 2 brown jumpers and 3 orange jumpers. Just like before, I'm going to take my time to twist these together to make sure that my breadboard doesn't get too crowded. By the end of this project, we're going to have wires going all over the place, so a little bit of cable management now goes a long way. The last thing we need to do is make the necessary connections to get 5-volt and 12-volt power where we need it to go. Both the Arduino and motor driver need 5-volt power. The Arduino has pins V-in and ground on rows 16 and 17 of the right side of our board, respectively. So to connect those, I'm going to plug my orange wire into J16 and my brown wire into J17, and then plug those into my 5-volt bus. To connect the motor driver to 5-volt power, I'm going to plug my brown jumper cable into pin J11 and my orange jumper into pin J12. Then I'm going to connect these two to the 5-volt bus. The motor driver also has a pin called standby. Unless standby is raised to 5 volts, the motor driver won't work. What we're going to do is take an orange jumper cable, plug it into pin A10, and then plug that into the hot line on our 5-volt bus. Remember that our motors are the only 12-volt components we have, but they get 12 volts through the motor controller. So that means we actually need to route 12 volts to the proper pin on the motor controller. We're only going to use one red wire, and that may seem confusing. Why don't we need a ground? Well, our grounds in this system are all common grounds, and since the motor driver is already receiving ground from the 5-volt bus, we only need to feed it 12 volts. To connect this, we're going to take 12 volts from the 12-volt rail, and we're going to connect it to pin J13 on the breadboard. The last connections we need to make are between the motors and the motor driver. To do this, I'm going to make myself a set of red and black twisted wires. On the motor driver, there are pins labeled A01 and A02, and also B01 and B02. We want to connect the motors to these pins because these are the output pins of the motor driver, hence the O. To do that, we're going to take our first set of twisted black and red wires, and we're going to plug the red into E1 and I8. So here's E1, and we're going to plug it into I8, and then the black goes into E2, and I7. And this can be a little tricky. This is why I say a little cable management goes a long way, because we are only going to put more wires on this breadboard by the end. Alright, to plug in the second motor to the motor driver, we're going to take our second pair of twisted wires, and red is going to go into F1, and then into I10. Oh boy. Black then is going to go into F2, and I9. By now, things are getting a little cozy in here, so it can be a minor challenge, but hold on. Perfect, there we go. Alright, it can be challenging to see where each of the individual wires goes in there, but I'm going to do my best to give you a look. In the Jupyter notebooks, we should have the same information on where exactly all these pins go, and also still pictures of this whole arrangement in multiple states of progress. So you may find it easier to follow the instructions on the Jupyter notebooks when you're plugging the pins in. Alright, that completes our rover's power circuit. When we return in the next lesson, we're finally going to get around to making our rover move.